Hmm? Okay. Mark, can you do me a favor? So, fan on. Not working. Then it's okay. Leave it. Leave it. Leave it. Okay. Uh, so this will be the last session in this course. So we are in week 12 and we will be looking at linear matrix inequalities. So we have already seen a few inequalities such as the Lyapunov, that is A transpose P plus PA should be negative definite and P is a symmetric matrix which is positive definite. So if this LMI is feasible, then you will get a, upon solving this you will get a P matrix. Okay. So, so you can write this as A transpose P plus PA is less than or equal to some negative definite matrix, that is the negative of the identity, for example. So you can, this kind of programming where you give where you have to solve for a P matrix which is positive definite, it's called semi-definite programming. Okay. So you are checking about the eigenvalues of a matrix. Okay. Not solving for the matrix itself, you have to make sure the eigenvalues are positive and things like that. So it's called a semi-definite programming. Okay. So there are various types of programming like linear programming which you would have come across. Then there is convex optimization. Okay, and there are different types of geometric optimization. There are so many things. So one of them is semi-definite programming. So usually in control theory you will see a lot of semi-definite programming for controller design and based on constraints. Even your LQR, it can be written as a linear matrix inequality. So what is a linear, so what's the definition of a linear matrix inequality? So let's say a function of p, okay, or x in general, it's a function of x which is equal to some known matrices x1, f1 plus f2 up to xn, fn is less than 0. This is where xi's are unknown and fi's are known matrices, okay, and you have to solve for xi. You have to find an xi such that this inequality holds, okay. So in your Lyapunov case, let's take a two-dimensional where A belongs to R2 cross 2, then A transpose P plus PA less than 0 can be converted to this. So this is called the standard form. So it can be converted to a standard form. So let's take a 2 cross 2 matrix. So that is, and P greater than 0. So how can I write this? So this is A transpose P11, P12, P21, P22, or this is again P12 plus P11, P12, A, okay. So I can write this as a, I can convert this into a linear matrix inequality where your x1 will be now P11, P12 and P22, okay, and solve for these three variables. So if you have a symmetric matrix, how many variables will you have? For a 2 cross 2 you have 3 variables, for 3 cross 3 you will have 6 variables to solve, okay. So that's, yeah, so that's how many variables you will have for a symmetric matrix and solving for an LMI. So let's take the system x dot equal to a plus b k times x. Now we have to solve for x also, k as well as p, okay. Find k and p such that where p is symmetric positive definite, such that a plus b k transpose p plus p a plus b k is negative definite, okay. So but the problem is this is no longer an LMI because you have a transpose p plus k transpose b transpose p plus pa plus p k. Now these two terms are not linear because they have a product in the unknown terms. So it's not a linear matrix inequality. So to convert, what we do is we change the variables n equal to some k into x, okay. So yeah, where x is equal to p inverse, okay. So now we multiply this entire equation by pre and post multiply by x. So you get x into a plus b k transpose plus a plus b k x is less than 0, okay. So this implies by substituting this you will get ax plus x a transpose plus b n plus n transpose b transpose and x is positive definite, okay. So these are the two LMIs which you have to solve. So in general case you can't always apply this trick, okay, of changing the variables. So we will have to look at some mathematical tool called the Schur complement, okay. So something called the, just a second, called the Schur complement. So let's take a matrix A which is block diagonal A11, A12, not block diagonal, block matrix. So let's say this belongs to R 2n cross 2n and each blocks have n cross n matrices. So if A11 is invertible, then the Schur complement of A11 is equal to A22 minus A21, A11 inverse A12. Okay. Similarly, if A22 is invertible, then the Schur complement of A22 is equal to A11 minus A12, A22 inverse A21. So, easy way to remember is, if you want to take this, start with the matrix diagonally opposite to it, then go in the anti-clockwise direction. Okay. So, that is how you get the Schur complement. So, now what is the importance of Schur complement? The thing is, determinant of A is equal to, so you can always write A is equivalent to A11 0 0 Schur of A11, or if A22 is invertible, then it is equivalent to Schur of A22 0. Okay. So, what is the determinant of A equal to? It is determinant of A11 times determinant of Schur of A11, and similarly in the second case it is A22 times Schur of A22. Okay. By equivalence, we say there exists a matrix, two matrices that are invertible, Q and P, such that B equal to Q inverse AP implies B is equivalent to A. So, it is a special case of transformations. Okay. If in case these matrices are not square, then the A matrix and B matrix are not square. So, you can't call them as similar matrices. So, they are equivalent matrices. Okay. So, you can transform one to the other. So, yeah. So, those are called equivalent matrices. Now, if suppose a special case when A is equal to A transpose. So, when A is equal to A transpose, the block diagonal will also be symmetric, that is A11, A12, A12, A12. So, this is a symmetric block matrix, and so if they are equivalent, we can say A1 A. So, we can write if A is negative definite, this implies A11 is negative definite and Schur of A11 is also negative definite. Okay. Similarly, in general case, if A equal to A transpose, then A is negative definite implies AII is negative definite for all I equal to 1 to R. Okay. So, that is a trick which you will use for discrete systems. So, we have the discrete Lyapunov stability, the Lyapunov equation or the Lyapunov inequality. So, for discrete time, we have P which is positive definite and A transpose P A minus P which is negative definite. This is same as writing M1 is minus P, P A transpose P and minus P. Okay. So, if I take the Schur of this, so since P has to be invertible, we are writing minus P is less than 0 or P is, okay, that is 1. And what is the Schur of this M1? So, Schur of P is equal to, so for the M1 matrix, Schur of P is equal to minus P minus A transpose P into P inverse. Okay. So, there will be a negative here. So, times P into A is negative. So, this is equal to minus P plus A transpose P A is negative definite. So, which implies A transpose P A minus P is negative definite. So, this M1 being negative definite is the same as this being negative definite. Okay. And if you see, this M1 has all linear terms in P. Okay. So, that is why this is Schur complement makes it easier to convert it to an LMI. Now, for the stabilization problem, which means again you have to find a k. We can write in terms of Schur complement minus P inverse A transpose plus K, okay, A plus BK. Okay. Now this is not an LMI. Even if you say minus P, okay, so this has, I think, less than 0. Minus P should be less than 0, implies P is greater than 0. Now if you take the Schur of P, this is equal to minus of P inverse minus A plus BK transpose, just a second. So A plus BK into okay. So this is same as writing. So it doesn't matter if I take this P or P inverse, right? So it is A plus BK some P bar transpose minus P or P bar is less than 0. Okay. So this is same as writing A plus BK transpose P bar. Since I am just taking the transpose here, minus P bar is less than 0. So taking the transpose does not change this negative definiteness, okay, because everything is symmetric in this case. Okay. So that is for the stabilization, but if you see this, I will call this M2. M2 is still not a linear matrix inequality. So we convert by replacing K equal to NQ inverse, where Q is P inverse. So now if I do that, I will get minus Q on both sides and Q A transpose plus N transpose beta, and similarly this will be AQ plus BN. So for solving all this, it is not trivial by hand. Even for 2 cross 2 it is difficult. So what you use is some solver, usually MATLAB. So you can use solvers based on MATLAB. Those are usually YALMIP, or you can use CVX. So CVX is usually for it has all. So these two solvers can be used for both. So convex optimization, linear programming, and other things like semi-definite programming, SDP, etc. So there are so many other types of programming which these two enable, and they will have some solvers like Mosaic or Sedumi. So these are the solvers which these packages use to solve the optimization problem. Okay. So we will also see that in this lecture. So next we will see an example. I think it is there in the lectures as well. So we will take an example. Let us take an LMI given by 0, 1, x1, x2, and 1. So this is my LMI. I want to check when it is feasible. Okay. So when is this feasible? So I know that this is invertible. Okay. So if I do not have any Schur complement with me, I do not have the knowledge, how will I check? I will have to check if eigenvalues of this. So I will have to write lambda minus 1, etc., and it will have some terms in x1 and x2 is greater than 0. Okay, for all. So I have to find x1 and x2 such that all the lambdas are greater than 0, the real part. So instead, if I have Schur complement, it is easier. So because I know, I will call this A11 is the identity matrix. Okay, A22 is equal to 1, A12 is x1, x2, and these need not be square. A21 is x1, x2. Okay. So what is the Schur of A11? Okay, so Schur of A11. So this is a symmetric block matrix because this transpose is same as this. Okay. So what is the Schur of A11? So Schur of A11 is equal to 1, so 1 minus x1 x2 times identity times x1 x2. Okay, so identity inverse is identity itself, so this is 1 minus x1 square plus x2 square is greater than 0, which implies x1 square plus x2 square is less than 1, so which is a region inside a unit circle. So it's this shaded region. So if you pick x1 and x2 that is inside the shaded region, it will always have a eigenvalue which have positive real part. Okay, so that's the meaning. Now let's say we have another constraint. So let's say these are the constraint for maximum fuel. Okay, so if you want to minimize the fuel, and this is the maximum fuel you can use. Okay, then or let's say this is the maximum deviation state which you can go, but now you have another constraint which tells you can only use fuel that is less than, let's say, 1. Okay, so you have to write it separately, and then you can just add this to the existing LMI. So that will be x1 x2 x1 x2 0. So this was 1. Okay, and you have to write u minus 1. Okay, this will be 0 u minus 1, or I'll take 1 minus u is greater than 0. Okay, so this can be written as an LMI. So there are some rules which you can use to simplify LMIs. So if f of x is positive definite, this implies minus of f of x is negative definite. This is quite obvious because the eigenvalues swap their signs. So next is if f of x is less than, so this implies, so what this means is f of x minus g of x is negative definite. Okay, and similarly if f1 and f2 are negative definite, then you can write it as a block diagonal constraint. Okay, and finally if A, B, C, D is feasible, then D, C, B, A is also feasible. Okay, so this is just rotation of this. So if you rotate, so by rotate I mean A, B, C, D times the matrix 0, 1, 1, 0. So what you will get is so this is just swapping the rows. So 0, 1, 1, 0. So this is nothing but B, A, D and C. So now if you pre-multiply, so if you now pre-multiply, you will get, D, C, P, A. So this is something like a rotation. Okay, it's just a similarity transformation, which means it doesn't change the eigenvalues. So that's the, yeah. So these are the rules which you can use for solving LMIs. Now where do we come across in in control, come across LMIs in control? So the first one which we discussed was already the Lyapunov stability and controller design. Next is something called DR stability. So let's say you are working in discrete time, x of k plus 1 is equal to Ax of k. So I am not giving control inputs as of now. So and I give you a region defined by the set of all complex numbers such that R11 plus R12z plus R21 z star plus R22 z star is less than 0. So, this is the region I give in a complex plane. So, this is my complex plane. So, sigma, and I will call this j omega, where z is equal to sigma plus j omega. Okay. Now, I define a region like this. So, where R11 are all matrices. So, I can define a region like, for example, let us take the unit circle. Okay. If I take the unit circle, so this is, I think there is a Z also here, I think. So, this is the unit circle. So, for unit circle I can write R11 is equal to minus 1, R22 is equal to 1 and R12 is equal to 0. So, what will that be? dr equal to set of all z in complex plane such that z star into z minus 1 is less than 0, correct. So, this is same as magnitude of z less than 1, which is a circle. Okay. So, this is a circle. So, similarly you can if you want to shift the circle, you can always write dr equal to z belongs to C, where let us take R12 equal to 1, then it will be minus 1 plus z star plus z norm z square is less than 1. Okay. So, this is like I give a shift in the real value. If I want to shift it in the imaginary value, I have to give z minus z star or something like that. Okay. So, that is the, these are called dr stability regions. Now, I can define regions like, you know, a circle here, a smaller circle here. So, what do these tell me? So, these are my locations for the eigenvalues. So, depending on my performance that I need, my eigenvalues, if I bring closer to origin, so if I am near the unit circle, my eigenvalues, then it is less stable or more oscillatory, and if I am closer to the origin, it is more the response is faster and it decays faster. Okay. So, and if you place them all at the origin, then I know that all my system, the system response will decay to 0 in one step. Okay. So, because xk plus 1 equal to 0 times xk, so which means xk plus 1 will go to 0. Okay. So, that is the thing. So, that is called dr stability, and dr stability implies all the eigenvalues of A are inside the dr region. Okay. So, how do you check for that? So, let us take A belonging to R n cross n. So, it is dr stable if and only if there exists a positive definite matrix P such that R11 Kronecker P plus R12 Kronecker PA plus R12 transpose Kronecker A transpose P plus R22 Kronecker A transpose PA is less than 0. Now, this is a linear matrix inequality because all of them have linear terms in P. Okay. So, is negative definite, and by Kronecker product we mean something like a element wise operator. So, you multiply each element of the first matrix by the second matrix. So, now this will be, let us say A is in n cross n and this is in m cross m. So, or it can be any other, it can be a rectangular, but for this, so this will be an nm cross nm matrix. Okay. So yeah, that is the, is it n? Yeah, it is nm cross nm matrix, or in this case it is 2 cross, yeah, 2m cross 2m matrix. Okay. So that is the Kronecker product. Now, how to check? Again we will have to use MATLAB because you can't compute all these by hand. And next application is let's say you have a system, x dot is ax plus bu. Okay, so you have a system, you have a output, or you have all the states, okay, and you have an input. Okay, so this is my plant, and then I have a controller and a computational where computational some interface or some communication channel, for example. So if everything is perfect in the ideal world, it's your input will have no delays. Okay, but usually because of the communication channel or the computational delay, the system the input will have some delay in it. So that is u t minus tau equal to k x of t minus tau. Okay, so it won't enter instantaneously. Okay, so you will always have x dot equal to ax plus b k x of t minus tau. Okay, so this is same as writing some ax plus ad times x of t minus tau, where d is now your delay matrix. Okay, so now for some systems, so how can you say the system is stable? The necessary condition for this is when A should be Hurwitz. Okay, A must be Hurwitz for the entire system to be stable. That's a necessary condition. Okay, the other thing is, so will this delay cause any problem in the stability? So that depends on the matrices A and AD. Okay, and how much delay the system can handle. Some systems are stable independent of delay. So that's the first case, independent of delay. And the second, depending on delay, there is a stability margin. So it's called some sort of a delay margin, and that's where you have all your phase margin, so that you can incorporate more delay in the system. Okay, so dependent on delay. So you have some delay margins also. So and in some cases this delay is dependent on, is time varying. Okay, at some point of time the delay is less, and some point of time delay is more, and you will have to tell how fast the delay changes also. Okay, so this case we won't be looking because it's a bit too complicated to solve using LMIs, but let's take the first case when it is independent of delay, meaning you have stability independent of delay. So theorem is, there exists a P and S both positive definite such that A transpose P plus PA plus S PAD AD transpose P minus S is negative definite. So what does this tell me? A transpose PA plus PA plus S is this. So this is your usual Lyapunov condition. That's like a necessary condition, right? And what does the other part tell me? It's the Schur of the Schur of this, right? So we can take the Schur of this or yeah, we'll take the Schur of this. So this is nothing but A transpose P plus PA plus S minus PAD S inverse AD transpose P is negative definite. So which implies PAD S inverse AD transpose P. So this is the second condition based on the Schur complement. So the first one doesn't have any delay term, it doesn't care what the delay is, and the second term has this delay term. Okay, so even having delay, it should be negative definite. Okay, so this in some sense incorporates the energy in the delayed values. Okay, so even having this delay, you need to have some negative definiteness. So and you can see tau does not enter the entire LMI, so it's not dependent on tau. And in the second case, we'll see an example using MATLAB. In the second case, delay dependence. Okay, so you can write, there exists a P, there are a few matrices that are symmetric. Okay, So I will write belonging to some Sn, okay, n cross n. So it's a symmetric matrix, okay, such that I have a block matrix M minus PAD into A minus PAD square minus A transpose AD transpose. So all of these are symmetric, that's why you can directly write less than 0. Usually you write it for symmetric matrices only, negative definite, because their eigenvalues are purely imaginary, purely real. So you can usually write it for only symmetric matrices. For non-symmetric also you can write definiteness, but that will only mean that will only say how the bound on the real values, okay, the real part of the eigenvalues. So that is minus A transpose times P A square transpose, okay. So this is a block matrix where M is equal to 1 by tau. So this is where the delay enters, 1 by tau P into A plus AD plus A plus AD transpose P plus, so this is the matrix. So this is where my delay enters. So I can check for different values of delay. I can always write some sort of a maximizing tau such that this LMI holds, okay. So I can write a program which says maximize tau, which such that this LMI holds, so it will give me the maximum delay. So yeah, this is about delayed systems. Now the third application is in checking if the system is passive, okay. So what does passivity mean? So let's say you have some system, okay. So if you have a system, it has 3 components, right? One is the input, one is the output, and the storage, okay. There is some storage here, okay. So you have some sort of a continuity or conservation theorems, right? For example, let's take a mechanical system, okay. So usually the input is force and the output is velocity, okay, usually. So what is the power? Power is force times velocity, okay. So that's your input power, okay. So input power is equal to the change in storage plus the dissipated, correct. So this so this you can write it as, so instead of writing this way, I am writing the change in storage is equal to the supplied power plus the losses, okay. So losses can be due to friction, so I will just write losses here, okay. And this is always less than or equal to supplied power if the losses are, if the system dissipates energy, okay. So H dot, or I am calling this H, or in some books you will see it as S. It is called the storage function. Storage function depends on your states, okay. It is just like your Lyapunov function. So you can write for linear systems as a quadratic storage function X transpose Px. So H dot or S dot, I will use the same terminology, is less than or equal to force times velocity or your input power or your supply rate. It is called a supply rate, okay. So there are various ways of defining this supply rate. The most common is something called the QSR supply rate, where you have some matrices. So YU times this matrix which has Q, S and R values times Y and U, okay. So in general we can just use U times Y 0 1 1 0 Y U, okay. So yeah, so this is the supply rate, and when the system is dissipative it is automatically stable, okay. So you can write an LMI for this. So dissipative, if the input is 0, okay, then S dot is less than or equal to 0, right? So which means the system is Lyapunov stable. Okay, so that's the thing. And you can also make it dissipative, control using dissipative. So if I take f equal to minus v, okay, then S dot is less than or equal to some minus v square. For a linear system, this means that your energy in the system keeps decreasing at a rate less than or equal to at a rate higher than or equal to v square. Okay, so your dissipative systems is automatically Lyapunov stable. Okay, so that's the thing. Now, how do you check if the system is dissipative? Let's say you have x dot equal to ax plus bu and y equal to cx plus du. So your A matrix tells you the stability part, and B and C relates the input and output part, okay, and D also. So you can write an LMI A transpose P plus PA, that's your Lyapunov stability, and the other case your input output to compare with the supply rate, you can write this in terms of PB minus C transpose and minus D transpose is less than or equal to 0. Okay. So what does this imply? This implies A transpose P plus PA. So let's take the case when D is 0. Okay. So when D is 0, which is usually the case, then you can only take the Schur of A transpose P plus PA, because this is not invertible. Okay. So this means A transpose P plus PA is less than or equal to 0, and 0 minus B transpose P minus C times A transpose P plus PA times PB minus C transpose is less than 0. Okay. So I can always write this as PB minus C transpose A transpose P plus PA B transpose P minus C. Okay. So something like this is greater than or equal to 0. Okay, or I'll write it here itself. So which implies B transpose P minus C A transpose P plus PA PB minus C transpose is greater than or equal to 0. Okay. So what is U into Y? U transpose into Y equal to U equal to that is equal to U transpose. So what is your supply rate? S equal to U transpose Y plus Y transpose U. So when you expand this, okay, so yeah, so you will get something like this equation. Okay. So this is how you test for dissipativity. Now, yeah, so I think, yeah, these are the examples. Now I think we will go to MATLAB to check how to how to use LMIs to solve for all these examples. So I'll share it on MATLAB. So firstly, you will have to install something called YALMIP. So maybe we can check that out first. So if you just go to their website, so this is, so you'll have so many. So if you check the tutorials itself, so there are so many types of programming like linear, quadratic, second order. So we have to go for semi-definite programming. Okay. So semi-definite is what you usually use. where the inequalities are like semi-definite, or you are basically checking for the signs of eigenvalues. Okay. And the one thing is, you can't use non-strict inequality, which means it has to be less than or equal to or greater than equal to. So what you do is, to ensure strict solutions, you will have to give some sort of a greater than or equal to a positive definite matrix or less than or equal to a negative definite matrix. So this is so we'll first see how to see the installation. So this is, so it's pretty simple. Just download. You don't even have to download. Just open the folder where you have to install and just run these 4 codes. Okay. And second thing, after you install, you may require something called sedumi. So you'll have to install that also. So it's again same. You can just download from Git and you can run the MATLAB code. It will install. And the next thing is, you have semi-definite programming. So it's in order to write the code, you just have to first declare your A matrix. Okay, maybe we'll look at the code itself. So you have your A matrix, then B and C, which is not required right now. Then I have declared a variable. So SDP var is your SDP variable. I declare P as a 2x2 matrix. Now I have to give the optimization problem, that is P should be positive definite and A transpose P plus PA should be negative definite. Okay. Now I just have to give optimize P. So if I just run this, I just so you can always use CVX. So I will show that also. So if you have CVX, yeah, I think CVX was yeah. So this is CVX. So you can always download CVX. So they have some free solvers, and there are also paid ones which are usually more which are commercial. So you can always use the free solvers. So it's the same way you can download, and the coding is pretty much the same. So if you look at the documentation, there are so many ways to solve. For example, least squares, all these things you can solve. And yeah, so that's the thing. So now you have so we have solved this. Now what is the eigenvalue of A? So if I want to see the eigenvalue of A, both are negative on the negative half. So which means it should give me a feasible P. So they have not told me anything which is wrong, or let's change the A matrix, okay, and then rerun this code. So when I rerun this code, what I get is the LMI's constraints were found to be infeasible, okay, and if I check the value of eigenvalues of P, I get negative, which means it's infeasible. I cannot find a P which solves both these constraints. Okay, so that's the that's how you solve for LMI. Now let's take the case of D stability, okay, or DR stability. Okay. So now here I define A as this. Okay, A is so for me the A is 0.5 plus 0.5 j and 0.5 minus 0.5 j, and forget B and R. So R11 I am giving as minus 0.7 and R22 as 1. So which means I have a circle of radius 0.7 square. Okay, yeah, so radius is root 0.7. Okay, so a circle centered at the origin with radius root 0.7. Okay, square root of 0.7. So so I define the Kronecker and things like that using this. So MATLAB Kronecker. So maybe if I show A equal to 1 0 2 3 and B is, let's take 3 4 2 1. Okay. Then the Kronecker of A comma B will give me a matrix which is 1 times 3 4 2 1, 0 times 3 4 2 1, 2 times 0 3 4 2 1 and 3 times 3 4 2 1. So that's my Kronecker of AB. So I've given the LMI condition here, and this is F, so which is again P1 greater than this, and this matrix should be negative definite. So if I just evaluate this, so successfully solved, so it has given successfully solved. And what is the eigen value of P? This is equal, so these are my eigen values. Now let's change my dr value to, let's say, 0.1. So I am now inside a circle of 0.1. Okay. So if I run this now, so just a second. Okay, just a second, let me run it again. Oh yeah, so even if it says successfully solved, my eigenvalues of P are negative, which means it's not, that's because of the solver LMI lab I am using. I am not using SEDUMI. So if you use SEDUMI, it will, so you are saying, it says LMI lab is not compatible, so it's better to solve using SEDUMI. So this is not a feasible value. So so that's what. So this means my eigenvalues of A do not belong to the dr region specified by me. So now if I increase this to 0.8, it will work. So if I increase this now, I will get a P matrix which is feasible. Okay. Now next thing we will look at is delay. Okay. So I will comment this. Okay. Okay. Next we will look at passivity. Okay. So let's it's the same way. So I have defined a transfer function. Okay. So my transfer function is, so if I just run this, so TF of numerator comma denominator. So I will get a transfer function 1 by s square plus 2s plus 4. Okay. So I have converted that to state space, and I have declared P1 as my SDP variable, and M1 is A transpose P plus PA, PB minus C transpose, B transpose P minus C, and this. So now it's in the same way I have to optimize this. So if I run this, so these LMI constraints were found to be feasible, which means it is not, it's not a passive system. Now there is a property that passive systems will have a relative degree 1. Okay. So relative degree is the number of, in linear systems, it's just number of poles minus zeros, or number of denominator polynomial minus the degree of numerator polynomial. Okay. So now if I just run this by adding one more 0 to the system, now it's feasible. So if I check eig of value of P1, I will get positive. So which means it's a feasible LMI. So that's so again the system is passive. Okay, and in the next case we will look at delayed systems. Okay, I will just comment this. So now I have an A matrix. So if I'll just run these two. So I have a matrix and a delay system matrix, that is this diagonal matrix. Now I declare P and S the variables for my optimization, P to be positive definite, S to be positive definite, and I have given the condition, that is A transpose P plus PA, PAD, AD transpose P, and minus S to be negative definite. Okay. So you have to make sure you give this value correct, because now it's a block matrix which is 6 cross 6. Okay. So now if I run these three, so now it says it is feasible. So if I just check eigenvalue of P, these are all positive, which means the system is stable independent of delay. So whatever delay you have, the system is always stable. Okay. So that's the thing. Now if I maybe make changes here, let's take -2 here and run the same code. Okay, so this is delay independent stable. Now let's look at delay dependent stability. So you have an A matrix, a delay matrix. Okay, I have made a maximum delay of 0.2. I have declared two SDP variables x and beta, and so whatever we have discussed, I have given this constraints. X is positive definite, beta is some small value, and so this is the optimization problem. Now if I just run this, you can see all are negative. So which means eigenvalue of the feasible, this problem is negative. Okay, so which means I have solved this problem. So what is the eigenvalue of x? So we have to give value of x instead of just x, because x is a SDP variable. So you can't find the eigenvalue of SDP. You have to give the so it's a different structure. So you'll have to give eig of value of x. So this is positive now. So which means for a maximum delay of 0.2, the system is stable. Now if I increase it to 0.8 and run the same thing, so I do get some eigenvalues positive for m, and what about the other one? So it's not feasible. So m has negative eigenvalues, so which positive eigenvalues, which is not desired. We need m to be negative definite. Okay, so which means the system cannot handle a delay of 0.8. Let's check for 0.4. So again the eigenvalue of m is again positive, so again 0.4 won't work. So yeah, 0.3 works. So you can actually find some sort of a bound on the maximum delay the system can handle. Okay, so yeah, so these are the, so I'll upload these codes to the drive folder. Maybe you can have a look at it. So yeah, so these are the things which you use LMIs to solve, and there are other things. I think the references are there in the website, so you can have a look at that. And so there are other uses of LMIs, like for example, while designing controllers for any linear system or any type of controllers, you can always use LMIs to solve that. And yeah, so these optimization problems optimize the eigenvalues of the system. So that's why they are called semi-definite programs. And yeah, so they are usually not convex, and they can have multiple solutions as well. So they may not, for example, the P matrix is not unique always, right? So that's why it's not a unique matrix. So yeah, so that's it. And maybe if you have any doubts, you can post it in the forum. Yeah, so that's